Well, they hung up before I got to the phone, anyways. Maybe I can wrap this up with this podcast because I have to run to teach my class. As I said, just comparing 2 months in two very close years can be misleading because you have interannual variability, maybe multi-year variability that we talked about. Maybe you have natural modes like El Nino affecting things in one year versus the other. But nonetheless, you always want to keep your mind. This is about keep your eyes on potential changes that are trending. This is about ice thickness as opposed to ice extent, and this is another figure of the Arctic wide sea ice thickness calculated using a model. So you don't always have data. That's another thing you have to keep in mind, because the uncertainties in the computed sea ice thicknesses versus actual observations can be, fairly large, especially because in the models you're translating global warming, ocean circulation into ice building and ice melting. How accurate are your simulations? So nonetheless, you can see here ice thickness has steadily decreased, 80s, 90s, 2010s, and then 2022 here, which is somewhere in the middle of the 2010s decade, but you can see that it jumps out here in the winter months. So you can do comparisons of summer months versus winter months and all those good things. The whole entire story is, of course, if you look at interannual variations in the mean extent of the mean year sea ice, year sea ice in the Arctic. Okay, whatever that is, extent in millions of square kilometer. Sorry, millions of kilometers squared in the Arctic. So you can see that there is a very strong trend and there is a strong interannual variability as well. So you can follow up on the details. So this is for the Arctic Ocean domain that we talked about. So you have decreasing multi-year ice. So 4+ year old ice is almost gone. 5+ years will look even worse. 3-year ice is decreasing, and then you have 0 to 1 year ice becoming more and more dominant in the later years here by 2020, where the data stops. You have large part of it is just year-to-year ice, 0 to 1 year ice, which is what we said when we which is what we meant when we said that Arctic ice may be becoming much more seasonal, which is similar to the Antarctic sea ice, which builds up and melts away seasonally. So 0 to 1 year ice will be the largest fraction there as well. Other than that, the mean thickness itself is smaller because open ocean versus semi-enclosed ocean. This is seasonal sea ice speed, which I won't show. Tremendous scatter, but some trend lines exist. This is the Arctic sea ice drift speed between 1979 and 2019, decomposed into seasons. So you have spring, summer, autumn, and winter. So you can see winter has autumn and winter have large trends. So the exit paths out of the Arctic can obviously be problematic. This is about tracks of tabular icebergs larger than 5 square kilometers around Antarctica during 1992 to 2019 period. This is done using scatterometer data. If you don't know what that is, don't worry about it. This is the anomalies of the maximum sea ice concentration in September 2019 relative to 1981 to 2020. The main message I would take out of this is there are positives and negatives. So the ocean that traps the Antarctic here makes life complicated because the impact on the warming of the ocean and the moistening of the atmosphere and the large eddy activities here can be tricky. Okay, so obviously there is more iceberg carving going on in some places than in other places, the Weddell Sea sector and so on. Just briefly, what are the mechanisms? If you look at contribution of each of the 5 considered factors in percentages to the variability of sea ice area in the Arctic, the summation is 25%. The rest of the 75% can be attributed to atmospheric temperature fluctuations. So this is meta-analysis, so they are just taking data that's published and trying to synthesize them. So contribution to each mechanism, here is the total: 25% coming from ice albedo feedback. There are water vapor feedbacks, which is related to cloud response, and there is a debate about whether ice albedo feedback can explain all of it, but obviously water vapor has a very strong response. As you keep warming the Arctic with Arctic amplification and polar amplification, over time the dominant factor can change. This is the mean. So you can imagine that it may have started as the ice albedo feedback, but as the atmosphere got warmer and water vapor kept growing, then you started to get cloud feedbacks as well. And there is of course wind speedback, which is negative, and oceanic heat transport. There is a so-called Atlanticization of the Arctic, where more of the Atlantic is coming into the Arctic warm waters mostly, and you also have the entire idea of how the heat balance itself is changing in the Arctic. So that's something to keep in mind. This is the sea ice extent again, so you can see aerial export through the Fram Strait and the Arctic wide sea ice extent in mid-September. So that's crashing here. This is what is very alarming. So you can see aerial export through the Fram Strait through in March and August. Is it increasing? Looks like it's decreasing here, but you have to just be sure that the net sea ice extent is still decreasing, and sea ice thickness, as best as we can estimate from models, is decreasing as well. This is the monthly average total sea ice and mean year ice area flux from 5 gates shown in. So we saw the 5 exits and entries into the Arctic. So obviously all here and all gates and Fram Strait. So Fram Strait is explaining almost all of the sea ice drift. As for the Antarctic, of course, we know there is a strong Antarctic circumpolar current, which plays a critical role just in terms of isolating the Antarctic and giving it special dynamics, including the polar vortex and the ozone hole and so on. But if you look at the number of carved icebergs in the Antarctic region between 2005 and 2020, there was a jump and then it hasn't come back down. So carving events almost doubled here, exactly 125 to 50 or so, and you can also see there are El Nino impacts. So the bluish color marks the period of a weak El Nino, and the pinkish one is a strong El Nino that I mentioned before. When you compare just 2 years, you have to be careful about how these can affect. And there is another effect. If you hit the process of carving at the wrong time, then you may just move it to a new state and keep it there, or maybe this will come back. Of course, we have had a big 2023-24 El Nino as well. So we have to see what this will do or what it has done since the last data that is shown here. Let me just read off the summary briefly. Arctic sea ice has been monitored and modeled over the past 4 decades, and the results confirm the substantial reduction in ice extent in summer and thinning in winter, and a stunning rate of depletion of the oldest and thickest ice. On the other hand, Antarctic sea ice has shown no statistically significant change in the sea ice extent, and no apparent change in the ice type or thickness has been observed. Sea ice in the Arctic region is far more sensitive to climate change than the ice in the Antarctic, as we already said. This study offers an answer to the question posed in the title of this paper: why does Arctic sea ice respond more evidently than Antarctic sea ice to climate change? The answer to this question has been compiled by reviewing the geographic, climatic, and physical characteristics of the 2 polar regions obtained from a set of relevant publications. Couplings between sea ice and environmental processes are also investigated, which include atmospheric and oceanic forcings in each polar region. I skipped a lot of these details. And also the ice advection out of the Arctic basin and the floating icebergs within the Antarctic sea ice. Understanding the interactions between sea ice cover and those environmental aspects reveal clues for the answer to the posing question. Uh, I should have been more careful. When we say iceberg, we are talking about calving of the shelf ice, and here we are focused on the overall response, including iceberg calving increases and sea ice losses, right? Several elements that compose the answer are presented in this paper. While elements of the answer are presented in different parts of the text, a summary version is presented here. So I skipped the details, but we'll read the summary here. Global warming affects sea ice directly through melting and indirectly through modulating atmospheric and oceanic processes. So both of them have oceanic tunnels and atmospheric bridges. In addition, it enhances the calving and floating of icebergs in the Antarctic region. While combining the direct and indirect aspects, the net impacts of climate change may take on either one of the following two courses. One is the instigation of a positive feedback cycle that enhances the warming and therefore the retreat of sea ice as observed in the Arctic. So that's ice albedo feedback. Or offsetting the impact of global warming, hence stabilizing the ice cover as observed in the Antarctic. As much as the prime impacts of climate change on the Arctic is manifested in sea ice decline, its impact on Antarctica is manifested primarily in melting the ice shelves and accelerating the calving of icebergs. These are two sides of the coin of climate change impacts on the polar region. Since Arctic sea ice has been declining area and thickness both at a high rate, research into causes through observations and modeling approaches has been active. No final answer yet. Ocean melting versus cloud feedbacks, ice albedo feedback versus cloud feedbacks. Less attention has been paid to the Antarctic sea ice because of its lower economic and environmental influence on humans, but it's also a rough place to go to. However, the importance of studying the influence of the increasing number and dynamics of icebergs on Antarctic sea ice is emphasized in this study. Icebergs are sources of fresh water as a result of basal and side melting. This affects sea ice formation and the subsequent properties. So, is the Antarctic surrounding ocean becoming fresher, making it easier to form sea ice or prevent the loss because of the warming? That has to be answered yet. The circulated question, which is commonly posted in the literature about why the Antarctic sea ice has not responded to the current climate change in the same way as the Arctic sea ice does, i.e. by declining and thinning, may not be the right question. A better version would be about how and why the current global warming has rendered the annual behavior of the Arctic sea ice to approach that of the Antarctic ice. Maybe that's related to the so-called Atlanticization, so more of ocean impact. In other words, the annual pattern of sea ice tends to minimize and eventually eliminate the presence of perennial ice, multi-year ice. Briefly stated, global warming is relaxing the entrapment of old ice within the Arctic basin and emphasizing the role of icebergs on sea ice in the Antarctic. Each polar region has its own peculiarities in terms of geography and climate. Therefore, researchers should not try to strictly apply conclusions regarding the impacts of climate change on Arctic sea ice to Antarctic sea ice. Let me stop here and run off to my class because I'm getting late. Okay, see you in the next topic. All right.